The graph of a linear equation is a straight line. Here's a linear equation, and here is its graph. Let's talk a little bit now about the steepness of that line. Different linear equations would have a different graph and therefore perhaps a different steepness associated with it. That steepness is called the slope of the line. Now, slope can be calculated. We can assign a number to the slope, and that number is assigned according to this ratio. The slope conceptually is rise over run from one point to another on a graph. Now, we can actually calculate the slope over here if we just pick a couple of points and count rise over run from point to point, like this point and, let's say this point. Now, from here to here, we're talking about a rise and run, you see. So the rise would be, let's see, from here, we go up 1, 2, 3, 4, and then we have a run of 1, 2. So rise over run would be 4 over 2, or 2. So the slope of this line is 2. Now, let's just talk about this slope number as we change the steepness of the line a little bit. You see, if we make that steepness greater like this, now, let's think about going from left to right. And thinking in that way, left to right, we're going uphill here. And going left to right, this would be downhill. All right, think about it like that. So if we're going uphill and the steepness is greater like this, it makes sense that the slope number would be larger, and indeed it is. Here we might be talking about a rise of 10 and a run of 1, so a slope of 10. And then steeper still, we might have a rise of 50 and a run of 1. You see, a slope of 50. So as slope numbers get larger and larger, it implies that the graph is becoming steeper and steeper left to right. All right, as the graph becomes more and more gentle, the slope number gets smaller and smaller. Here, if we're talking about this line, this graph, we would have a rise maybe of 4 and a run of 4. 4 over 4, oh, that's 1. So it's kind of going through the coordinate plane at sort of a 45-degree angle here. That's a slope of 1. It should make some sense that the slope number gets smaller and smaller as that steepness grows less and less like this. Here we might have a rise of 1 and a run of 5, a slope of 1/5. It would be no surprise then that as the slope numbers are big, 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 and then they get smaller, 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 smaller into fractions down here, that if we're talking about a horizontal line, the slope would be 0. That means a no rise, 0 for the rise, and the run, well, who cares? 0 over some number is going to be 0. Now, as we go into the downhill idea from left to right, again, it's no surprise that we're talking about slope numbers that are negative, because big positive numbers, then 1, and then fractions, and then 0, and then think about that on the number line. So we're going from positive numbers all the way to negative numbers over here. So here we're talking about a rather gentle slope that's kind of going from left to right, it's going downhill. So we have a negative slope, but a run may be, a rise of, rise, it's not rising at all, it's falling here. And we're thinking, well, how do we calculate this? Well, think about it like this. I'll just choose a point here and one here, just to illustrate the idea. Now, this calculation of rise over run can be made from any point to another, regardless of leftness, rightness, and that kind of thing. So if we're talking about going from this point to this point, rise would be, well, we actually fall. We go down 1, 2, 3, and then we go over 1, 2, 3. So the rise would be -3, the run is 3, so a slope of -1. Now you might say, well, is it the same if we calculate it from this point to that one? Well, let's see. We would have from here to here a rise of 1, 2, 3, and a run in the negative direction, you see, 3. So it would be 3 over -3 or -1 as expected. Okay, so we get relatively small negative numbers, just little negative fractions for a slope that looks like this, then -1 as we see here, and then big negative numbers as we have a slope that's kind of like this. Okay, now let's consider the situation of a vertical line. We considered a horizontal line a moment ago, and we said that a horizontal line has a slope of 0. Well, what about a vertical line? Now think about rise over run. From one point to another, the rise, like a point right here to a point up here, that might be a rise of 5. Now the run, gee, there's no run at all. So rise over run would be 5 over 0. But 0 in a denominator causes the fraction to be undefined. So the slope of a vertical line is undefined. All right, so that kind of covers all the bases. Now notice that we said that the slope of this line is 2. We calculated it here as rise over run from one point to another. Notice that in the equation, the coefficient of the x is also a 2. Now that's not an idle coincidence. Notice also that the y-intercept is at -3, and that this number is -3. That also is not an idle coincidence. It turns out that when a linear equation is written in this form, that we can read right from the nature of the equation the slope and the y-intercept. And then it's no surprise that this form of a linear equation is cleverly called the slope-intercept form. So slope-intercept form. It is a form of a linear equation that gives information about the slope and the y-intercept. Now, generally, this form is written like this. It's y equals mx plus b, where m is the slope, b is the y-intercept. Now, this form can be used in graphing. That is, if we know the slope and we know the y-intercept, then we can identify the place for the y-intercept, and then from there we can generate points to plot to construct the graph. So instead of using a strictly point plotting method, we can use the slope and the intercept. Let me show you how that's done. Here we have an equation, and the equation is not in the slope-intercept form, but we can manipulate it into that form rather easily. All we're going to do is solve for y. Subtract 3x on both sides, and we have 2y equals -3x plus 6. Now divide throughout by 2. Divide here by 2, and we have y. Divide here by 2, we have -3x over 2, and then plus 6 over 2. Now, we would want to see a distinct coefficient in this term, so we would think of this as -3 over 2x, and then plus 3. Now, the 3 tells us the y-intercept. So we come over here and we identify the y-intercept. And now we generate additional points to plot by using the slope information. Now, -3 over 2 can be written as -3 over 2 like this, or as 3 over -2 like this. Now, here's the way we interpret this. For this one is a rise of -3 and a run of 2. So, from this point, a rise of -3, that means down 3, and then a run of 2 means to the right 2. And then from this point, we can use that slope information, down 3 over 2. Then from here, down 3 over 2. You see, we can go as far as we want in this direction. Now, using this other fraction, the 3 over -2, we can go in the other direction. That is, a rise of 3 and a run of -2. Let's see, from our intercept, a rise of 1, 2, 3 and a run of -2 puts us here. Then 3, -2, and so on. So we can generate a lot of points to plot just by looking at the information about the slope. Now the graph looks like this. Consider a rather degenerate linear equation, y equals 3. There are a few ways to interpret the situation. One way is like this. If we're thinking slope-intercept, we can think of this as y equals 0x plus 3. So we have an intercept at 3, you see, and a slope of 0. So an intercept of 3 and a slope of 0, well, we know that a line that has a slope of 0 is a horizontal line. So it's just a line that goes through the coordinate plane like this. Now, another interpretation here, using the point plotting method, just think about it like this. Just think about setting up a table of values according to this degenerate equation. Now, for x being, let's say -2, how about 1, 5. You see, for these values of x, what is y? Well, our prescription would be to put these values of x into the equation and solve for y. But this says y is equal to 3. And it means y is equal to 3 no matter what x is, because there's no x in this to affect the value of y. So y is 3 for all of these, and if we plot the points, we get, let's see, negative 2, 3, 1, 3, 5, 3, you see. And then constructing the graph, we get the expected horizontal line. The idea of slope is there are a number of mathematical ways to interpret slope. I mean, this rise over run thing is a manipulative form for graphing purposes and so forth. But in terms of word problems, the slope information can be thought of as a rate. Now notice that in our slope idea, rise and run, it's like we're thinking how far up and down do we go for units left and right. So here, just between this point and this one, we are dropping 3 units for 2 units of run, you see. And if I sort of reduce this to a single unit, you see I am falling 1 1/2 for every horizontal unit. So I am falling at the rate of 1 1/2 units per, you see, per horizontal unit. All right, now, with that in mind, with that idea, we can make an interpretation in real-life problems and equations like this. Suppose we have something like a cost equation for some product, and that cost equation is 25x plus 3,500. Now, let's interpret this in a couple of ways. Now, what this means is that this is the cost for X number of items being manufactured. So if no items are being manufactured, if X is replaced with 0, the cost is 3,500. So that's kind of a fixed cost, a kind of a setup cost for this particular product. Now, if we make one of these items, then it's 25 times 1 plus 3,500. If we make 2, it's 2 times 25 plus 3,500 and so forth. And it turns out that this slope, you see, can be interpreted as a rate. You see, that is the additional cost per unit. You see, because every time we add another value of x in here, we tack on make x a little bit bigger by 1, we're adding another 25. So 25 is the cost per unit, you see, or the unit cost or the marginal cost for this particular product. So it's an interesting interpretation. Now, here's how we go about the algebra of calculating slope given a couple of points. Now, it's the rise over run idea, but rise is just a change in vertical distance. So it's no wonder that the numerator of our slope formula will be a difference in y values. And run is a horizontal idea, so the denominator is just a difference in x coordinates. Now, the subscripted 1s and 2s just tell us that these two y values are associated with 2 different points, and these x's are associated with 2 different points. And there's nothing magical about the 2 appearing first and the 1 second. We could have y1 minus y2, x1 minus x2. What you don't want to do is jumble these up. You have to have, if the 2 is here, then the 2 has to be here. 1 here, 1 here. Okay, that's the idea. Now, to use this slope formula, suppose we want to find the slope of the line containing these 2 points. Well, let's just pop the information in. Let's see, a difference in y components would appear in the numerator. So if we say this is y2, it just appears first over here. So this is y2 and this is x2. So we have 4 minus 7. And then in the denominator, a difference in x components, I'm using 3 minus 5. So the slope then would be, let's see, 4 minus 7 is negative 3. 3 minus 5, negative 2. So this is a slope of 3/2 or 1 1/2. Gee, we would expect that line to sort of be like this going through the coordinate plane. We can verify that. Gee, we can look at it like this on the graph. Let me just make a quick sketch here. And we have 3, 4. I had to jam these just a little bit because I don't have a lot of room here, but let's see, and then 5, 7. That's up about right here. So yes, indeed, this is about what we would expect, you see. A slope that is positive is sort of going uphill from left to right. And because it's 1.5, you see it has a little more steepness than the idea of sort of a 45-degree angle here, which would be a slope of 1. Often in the study of equations and their graphs, we start with an equation and investigate aspects of graphs. And then we follow that with information about graphs, and then we generate information about equations. We're going to do that here. We just talked about equations leading to graphs, lines, and their slopes. And now we're going to take information, graphical information, and we're going to generate equations. Now, that process involves taking the slope formula and rewriting it a little bit, just manipulate it a little bit into a different form. Now, I'm going to change the form here by clearing the fraction, and I clear the fraction by multiplying through by this common denominator, or I can think of simply cross-multiplying. Now, think of this as m over understood 1, and let's cross-multiply. So the denominator here is 1, and if we go this way first, we have 1 times y2 minus y1, and in the other direction, m times x sub 2 minus x sub 1. Now, when this form of the slope formula is used, the subscripted 2's are often eliminated. So this form is often written like this, and it's called the point slope form. Now, I like to think of the point slope form as a form of the slope formula. Really, it's a form of a linear equation, but I like to think of it like that, as a form of the slope formula, because if you forget it, you can always generate it from the slope formula. Now, it's called the point slope form. It's kind of a clever designation because it is most useful when you have information about the coordinates of a point and you have information about the slope. For example, suppose we know that the slope of a line is negative 2/3 and the line goes through the point 6,1, and we want to generate the equation of the line. Whenever you're asked for the equation of a line, think about this point slope form and just write it down. So we would begin with and now just plug in information that we know. We have the coordinates of a point and we have the slope. We know the slope is going to go in place of the m here. Now these are the coordinates of a point. We can use this xy pair either here or here. You see, we can plug into this xy pair or that xy pair and it will come out the same. But if you did it 10 times both ways, you would find that it's a little easier if you plug into this second xy pair. It's just easier algebraically. And that's why these subscripted 2's are often eliminated in this form. All right, so it's guiding us to plug into the right pair. Here we go, we have y minus. Now the y component is 1, and then the slope negative 2/3, and then x minus 6. And now it's a matter of cleaning it up and just writing this linear equation in a particular form. One way to do it is like this. Negative 2/3 times each of these, negative 2/3 x. We would have plus, and then 2/3 times this, the 3 and the 6 would cancel, leaving 2. 2 times 2, 4. So we would have this. And then if I want to write this in the slope-intercept form, that's the form where y is isolated on one side, remember, I would add 1 on both sides to find y equals negative 2/3 x, then plus 5. So now this is the slope-intercept form. Now, there's another form that we could write this in. We could clear the fraction, for example, and put all the terms on one side. You would clear the fraction by multiplying through by 3, and then we could kick all the terms to one side, and that would be a more general form for this equation. So the general form of a linear equation is where you clear all the fractions and put all the terms on one side. The standard form is this form, the form that we get information about graphing from. We get information about the slope and the intercept here, you see, and so we have graphical information, and therefore it's called the standard form. General form is more of an expanded idea. All right, so that's the notion. Now this situation, this discovery of the equation kind of process has a nuance or two associated with it. And those nuances involve generally the changing of the slope. If we had a slope of 0, then the first thing we should think about is that we have a horizontal line, you know, and we could go directly to the equation of this line, or we could use this point slope form. You see, if we use the point slope form, then m is replaced with 0, and this goes out, so we have y minus 1 equals 0, or simply y equals 1. Well, there's no surprise there. Gee, if we're thinking about the point 6, 1, which is, roughly right here, a slope of 0 implies a horizontal line, and a horizontal line going through this vertical level of 1. You see, vertical distance level of 1 means y equals 1. Now, in a similar way, another nuance involves a slope that is undefined. Now, if the slope is undefined, it really means that we can't use this. We can't use this point slope form, because when we put undefined in here, then the whole equation is undefined. So we have to throw it out, and we have to analyze the situation a little differently. Well, it's pretty easy to analyze, though, because we understand that a slope that is undefined implies a vertical line. So when the slope is undefined, we know that we have a vertical line going through this point 6, 1. Now, if we understand that a horizontal line going through this point is a line that is described as y equals 0, it should be no surprise that a vertical line going through this point would be x equals 6. You see, it means that x is equal to 6 for every y. So x is 6 when y is 1. X is 6 when y is 5. X is 6 when y is negative 2. You see, so for every y value, x is 6. So no surprise that it's a vertical line. Suppose we have this information, and we want to generate the equation of the line. Well, we have a couple of points. We still start the same way. We think we're after the equation of a line, so we're going to start with y minus y1 equals m times x minus x1. All right, and then away we go. Then we start to ponder the situation. Gee, the point slope form says we need information about a point. We have 2 points. And we need information about the slope. We have no information about a slope. So we have an abundance of point information, but no slope information. What are we going to do? Well, there are a couple of things that we could do. We could change this equation and rewrite the slope, the m, as y2 minus y1, x2 minus x1. Just put that slope information right here and make the calculation of slope associated with those 2 points right here in this formula. I kind of prefer, though, going out to the side and making the calculation for the slope like this. Now, I've got stuff written over there, so let's go back over this way. So you go to the side and you say, okay, I'd like the slope of a line going through a couple of points. And I know that that's a difference in y values over difference in x. And by the way, there's a notation that's used often in calculus. I'm going to use it right here because you're going to get to it in time anyway. But it's the notion of using a little symbol called delta. Delta meaning change, roughly. So change in y over change in x is what this says, let's say. Okay, so the slope then is, now the change in y, difference in y components. I'm looking over there and I see 1/2 minus 5/4. And the change in x components, I'm seeing 2 minus 1/2. See, this is kind of a handy notation, but you just have to make sure that you have an xy pair here that are associated with one another and the other xy pair over here. That's the important thing. All right, let's see. We have 1/2 minus 5/4. Now let's think through this a little bit. I don't have a great deal of room right here. This is 2/4. 2/4 minus 5/4 is negative 3/4. And in the denominator, I have 2 minus 1/2. That's 1/2, or 3/2. So this is 3/2. Now this means negative 3/4 times 2/3. 3's go out. 2 and a 4, 2. Negative 1/2. Okay, good. Now, negative 1/2. So now I have information about the slope. I'm going to put the negative 1/2 information right here. Now, what am I going to do, though, about the other stuff? I've got x minus something here, y minus something here. What xy pair do I put in here? Do I put this pair or that pair? Turns out, doesn't make any difference. So just take one that kind of looks easy. This one only has one fraction. Let's use that one. So we have y minus 1/2, and then over here x minus 2. And now we go through and clean up a little bit. This is negative 1/2 times x. That's negative 1/2 x. Negative 1/2 times negative 2. Negative times negative positive. 1/2 of 2 is 1. And now we'll add 1 on both sides. Excuse me, we'll add 1/2 on both sides to find y equals negative 1/2 x plus 1 and 1/2, or 3/2. So again, I'm putting this into the slope-intercept form. Now, once again, that when problems like this come at you, there are a couple of nuances which you can, again, take care of very, very quickly. If you're looking at the coordinates of a couple of points, try to notice when you have a situation where either both x components are the same or both y components are the same, and make an interpretation of that. Suppose here that this were 1/2. You see, so I have 1/2, 1/2, and then 1/2, 5/4. Now, the important thing to notice is that the x components are the same. Now, when the x components are the same, think about it graphically. I have an x of, let's say this is 1, so I have an x of 1/2 for one of them, and it goes up to 1/2. Okay, let's say it's here. And then an x of 1/2, it goes up to 5/4. 1 1/4, that's about right up here, let's say. So we have a vertical line. That's the important thing to realize. You can visualize that without writing this down. The x components are the same implies you have a vertical line. Slope is undefined. Now what happens? Well, we have to go into that little process that we talked about earlier about defining or thinking about the equation associated with a vertical line. Gee, that's an x line. It's an x line going through where? Well, it's going through 1/2. You see, so it's x equals 1/2 is the equation associated with that line. And you get to the answer right quick if you just think through it properly. Now, if the y components are the same, you see, if the y components are the same, then the vertical distances for both points are the same. So we have a horizontal line, you see, and again, we can get to the equation right quick without doing all of this business. Okay, those are nuances. Now let's talk about, just for a moment, the usefulness of slope. We looked at an equation a little while ago, but I want to show you a different kind. It's one where we take graphical information and we generate an equation, and then we make an interpretation about a question. For instance, Yahoo Incorporated in the year 1997 had a cash flow per share of 3 cents. In 1998, it was 30 cents per share. All right, suppose we want to use this information to generate a prediction about what may happen in some future year or some year other than these 2 years. It might be a previous year. It might be whatever. It might just outside the bounds of this information. Well, we can do that like this. We can think, well, we have 1997, a number associated with another number. So we have a pair of numbers, an ordered pair. Here we have another ordered pair. Now, let's configure these ordered pairs in such a way that we can introduce these graphically. Now, a good way to do that is like this. When you have years involved, try to come up with a basis year, a year where you're starting your evaluation. Now, the information is beginning at the year 1997. So let's let 0 stand in for that year. That is, let our basis year be 0, or the number associated with 1997 be 0. And therefore, the number associated with 1998 is 1. So now, instead of dealing with these big, big numbers, we can deal with rather simple numbers. So we have then the ordered pair 0 associated with this, and then 1 associated with All right, now we have a couple of points, you see, and we can think about plotting those points on a coordinate plane if we want to. We can establish the slope associated with these two. And all of that is possible right here. Now let's calculate the slope. We'd calculate the slope like this. We have difference in y's, difference in x's. We have 30 cents minus 3 cents, and then 1 minus 0. So we have 27 cents over 1, or simply 27 cents. So the slope is 27. Now let's go to the equation form. Well, gee, we can use this mx plus b because we have a slope. We calculated it right here. And we have the y-intercept. We have the y-intercept because we have, you see, we have the 0 and this number. So the y-intercept is at 0.03. The y-intercept is 0.03. So we replace b with 0.03 in our equation. Now we can use this equation to make a calculation for cash flow in a particular year that we don't have listed here. Like, for example, in the year 2002. Well, the first thing we need to do, though, X stands for a number of years from 1997. So 2002, gee, that would be 5 years. 2002 is 5 years from 1997. So let X be 5, and we have, let's see, 0.27 times 5. Okay, that's 1.38, or $1.38. Now, understand that graphically, we're taking information like this. Let's see, 0 is associated with 0.03, let's say it's right here. And 1 is associated with 30, and that's way up here. And so we have information that's right here. We're trying to make an interpretation of this graph. You see, we're kind of trying to make a calculation of where this graph would be in that year. You see, this is the year 0, 1, 2, 3, 4, 5. This is really 1997, 1998, 1999, 2000, 201. Okay, 2002. Okay, so we're doing this. Now, our graph, our information is right here. And we're making an interpretation outside of where our information lies. This is called extrapolation, mathematically. We're performing an extrapolation here. If we were making a determination of some kind that is between these two data points, like right here, for example, then this would be called an interpolation. Generally speaking, an interpolation is more accurate than an extrapolation. And it turns out that the farther from the data points that you get with your extrapolation, the less accurate your information is likely to be. So we need to kind of temper our information. I mean, as we found out here, this $1.38, it's a loose idea. It's just a loose prediction of what may happen in a future year according to what has already happened. But a lot of things can happen between now and the year 2002. We know that slope describes the steepness of a line as it passes through a coordinate plane. It should be no surprise that if two lines are parallel, they have the same steepness and therefore they would have the same slope number. So parallel lines have equal slopes. What about perpendicular lines? Now let's think about that a little bit. We can see here, I think pretty easily, that since one line is sort of going downhill from left to right and the other is going uphill from left to right, that one will have a negative slope number, the other will have a positive slope number. So the slope numbers will have an opposite sign. All right, now, what about the number part of it? Well, we have a relatively steep negative slope here, and let's think of this as -5, and I can think of it like this. From this point to that one, I would have a rise of 5 and a run of -1. Okay, now this one, though, a positive slope, would be relatively gentle, so the slope number would be small. And it turns out that from one point to another, we could think of a rise of 1 and a run of 5. That is, these slope numbers are reciprocals of one another. And more accurately, they are negative reciprocals of one another. So perpendicular lines have slopes that are negative reciprocals. Now, with that information, we can answer such questions as this. Find the slope-intercept form of the equation of the line that passes through a particular point and is parallel and then perpendicular to the line described by that equation. So think about what we're going to do. We have a given equation. This equation has a graph associated with it. The graph is a line. All right, now, we want to write an equation associated with a line that is both parallel and perpendicular to this rascal going through the point 2, 1. You see, going through that given point. Now, we begin the process by identifying the slope of this line. Now, we can do that by constructing the graph and then doing a rise over run, or we can just manipulate the equation into the slope-intercept form. Let's do that. Take the equation and solve it for y, and it would look like this. So I'm subtracting 2x on both sides. We get this. Divide through by -3, and then simplify. Here we have y then is 2/3 x minus 5/3. Now, the intercept we don't really care about, but this is very important. So our slope here is 2/3. All right. Now, that allows us to begin the process of coming up with the equation of any line that's parallel with this, because any line parallel with this will have a slope which is also 2/3. So for the parallel line going through a particular point, now remember that point was 2, -1. So we're inventing the equation of a line, so we use this point slope form. And now the y component, remember it was going through the point 2, -1, so the y component is -1, the x component is 2. And the slope of a line parallel to the one that we had earlier is that same slope of 2/3. And now we just clean this up a little bit, and we have y is 2/3 x minus 7/3. Now, for the perpendicular line, let's come back over this way. Let's come this way just for a second. If the slope of our given line is 2/3, then the perpendicular slope would be the negative reciprocal of this. So it would be -3/2. And this is the slope that we're going to use to generate the equation of a line perpendicular to the graph of this guy. All right, here we go. For the perpendicular line, we start the same way, and we plug in a very similar way. The slope is -3/2 this time, and the xy components are the same, the 2, -1, and then we just clean this up to find the equation of that line to be y equals -3/2x plus 2.